part in room number 3 is given by Professor Traian ILIESCU from Virginia Tech. Traian is professor at the Department of Mathematics at Virginia Tech, and his research is in mathematics of turbulent flows. Roughly speaking, he creates models, develops algorithms for these models, tests them, and proves theorems, as he wrote in his webpage. So his current research deals with the development of reduced order models for realistic turbulent flows in engineering, geosciences, and medicine. And today he's going to talk about large eddy simulation reduced order models. So please, Traian, the floor is yours.
Thank you, Andrea. Thanks, Andrea, and thanks to all the organizers. A big thank you to all the organizers for putting this together. It's a great pleasure to give a talk in this session. I changed a little bit my title. So the initial title was Data-Driven Variational Multiscale Reduced Order Models, and I will talk about that. But I decided to go a little bit bigger and talk about large eddy simulation reduced order models. And really, so this is going to survey. I know I only have 15 minutes, and I'll try to survey the work of our group over the past 2 decades. Really, these are 2 distinct research fields. One is large eddy simulation. This is a very pretty well-established research field, and reduced order modeling, and that's also well-established. And I just want to talk about connecting the 2. I think that this is an interesting research direction. I'll talk about turbulence mainly, but by turbulence, I mean fully developed turbulent flows like engineering, geophysical flows, but also transitional flows. And those can be encountered in biomedical applications, cardiovascular flows. So I think these models that I will be talking about will be relevant to cardiovascular flows. At least that's what my friend and collaborator, Alessandro Veneziani, is telling me. Okay, so this is the sales pitch. So the sales pitch is that I will talk about principles. What I'm interested in is showing you what, why, and how, okay? And I will not put such an emphasis on models. I will talk about them, I'll present results, but that's not the main point. The main point is to understand the principles. I really think that's important. Okay, so that's the outline of my talk. First, LES ROMs, what they are. I just described the main framework. Then that's what my original title was, Data-Driven Variational Multiscale ROM. Because this is the model that we're really excited about, and that's what I've talked about most. And then end up with some conclusions. These are my collaborators, and so that's a lot of work we've done over the past 2 decades. These are my former student, Chang Hong, now is going to Wisconsin, and Bigil, she's at Cecile working with Tomas Chacon-Nebolo. Okay, so without further ado, let's start talking about LES ROMs. Okay, now LES, I'm not going to talk too much about it per se. This is a well-established field, as I said. This would be a good starting point. So Pierre Sago's book, you find hundreds, not thousands of models. Okay, we've also done some work 2 decades ago on mathematics for large eddy simulation. So well-established field. Okay, now for when we are talking about Galerkin ROM, this is at least the type of modeling that the sort of modeling I'll be presenting. It's a very general type of approach. You start with an equation of the form U sub P is equal to capital F of U. You use Galerkin expansion, a projection right here. Yeah, so we project onto the modes 1 through R. I'm preaching to the choir. You've seen this before. And then voila, we get the Galerkin ROM. Simple, very simple. It's a Galerkin procedure, but with smart basis functions. So chosen very well. At the end of the day, we get a dynamical system. A dot is equal to F of A for the coefficients of our expansion. Very simple. For the Navier-Stokes equations, this dynamical system is very simple. A dot is equal to matrix A times A plus A transpose BA. I'm assuming incompressible flows, so no pressure model. That's very important in applications, but I'm not going to talk about this here. Okay.
The back of the initial traveling wave, and this creates a pair of counter-rotating spiral waves. Right. So this procedure is
different settings, an healthy one taken from previous works, and the pathological one which tried to resemble as best as we could the characteristics that we were.
I'm looking at under-resolved numerical simulations like turbulent flows or multi-scale phenomena. I think when you have multi-scale phenomena, you usually often see this type of behavior. And I will try to advertise largely simulation problems. So what is that? It's a very simple principle. So basically, you take a spatial filter. In reduced order modeling, the projection is the most used spatial filter, but we use the differential filter, so other filters as well. You filter your variables, and by filtering them, you only keep the largest scales that are, cheaper to model, easier to model. You use the filtered equations, and you solve for the filtered variables. So filtering, spatial filtering is important. At the end of the day, however, what you get is pretty much your Galerkin ROM plus a closure term. And there are many ways of, so that's a correction term to account for the effect of the discarded modes. And there are many ways of modeling this closure term. Again, in LES, you have hundreds, thousands of models. In reduced order modeling, there are quite a few, but not as many. And you see here a list of people, and the list is not exhaustive. So we didn't, I just tried to kind of give you an idea about people involved in closure modeling. There are LES type of modeling and non-LES type of modeling. And I would classify the closure models as functional. I use the same terminology as Pierre Sagot in his LES book. So functional means that the closure model should mimic the effect of your actual closure term. So it's functional. The structural models are different. So the structural models try to match mathematically the closure model. Yeah? So not its effect, but the actual model. And there's a third class that Pierre Sagot did not mention in his 2006 book, and this is data-driven closure modeling. And this is a shameless plug. So I'm advertising our recent archive paper on data-driven closure modeling. This is with Omer San and his group and Bern Noack. We try to survey some of the most recent approaches based on data. So functional, structural, and data-driven. Okay, so functional would be, classic example would be eddy viscosity ROMs. So here, this is one of our Kamami papers, 3D flow past the circular cylinder. And you can see that pretty much eddy viscosity models on the average. So if you look at the spectrum, and if you look at the state-of-the-art LES model, that's the dynamic subleast scale model. So we can do a pretty good job, much better than pure Galerkin ROM or even mixing length. Okay. A different type of modeling is the structural one. In this case, we use a spatial filter, not a projection. That's where it is classic, but a spatial filter, the differential filter right here. And we use techniques from image processing, like regularization, to come, like Laurentiev regularization, to come up with a deconvolved, approximate deconvolved variable W of the unfiltered as an approximation of the unfiltered flow variables. We need this in the closure term. So this is mathematical. It's just we deconvolve the filter variable. Yeah? This is from 2017 paper. This is quite a neat model. Has nothing to do with eddy viscosity. Okay, so I don't have too much time. What I want in the next 4 minutes or so, I want to talk about the model that I'm pushing hard, and this is the data-driven variational multiscale model. This is based on Tom Hughes' work and his group's work from 2 decades ago. It's simple and general. Uses the projection to separate the scales. First, we take the first modes, these are the large scales, and the last modes are the unresolved scales. And this gives you a 2-scale decomposition, right? So resolved and unresolved. You can do a 3-scale, and we've done that decomposition, the same type of technique. Okay, so what do we do? What we do is summarizing this algorithm. So let's say that we have a lot of modes that think about turbulent channel flow or turbulent flow, but we only want to keep 10 modes. Yeah, so under result. Well, how do we model the closure term? Yeah. So what we use is data. So we use the actual full order model data, and we compute the actual closure term with full order model data. And then we take an ansatz. Now our ansatz is an A tilde times A plus A transpose B tilde times A. So we pretty much use the same ansatz as the Galerkin model, but you can use a cubic term and so on and so forth. After we find this A tilde and B tilde, we correct our Galerkin term. This is it. Okay? The question is, does it work or not? Well, it works. Now, I want to show you some results for the 2D channel flow. I chose a very the bad results for the 2-scale model, and that's when the 3-scale model actually produced an improvement, the one improved. So it does work for in the predictive regime for the 2D channel flow, 2D flow past the cylinder. Sorry. Then we said, okay, can we do better? And I think that what helped us was using physical constraints. So overall, we want to make sure that the closure term does obey the physical laws. So it dissipates energy on the average, and imposing these constraints does help us. This is, again, for the 2D flow past the cylinder, using the physical constraints in red does improve the results, okay? Next problem is, so I have 2 more minutes, I guess. Yes, 2 more minutes. So next problem is the quasi-geostrophic equations. These are equations modeled in the large scales in the wind-driven ocean circulation. And you can see these gyres here and here in the North Atlantic. Yeah. And we use the problem from Graybach and Hadiga that displays a 4-gyre pattern. The Galerkin ROM does not recover it. The data-driven VMS ROM does recover it, but adding the physical correction improves the accuracy of the results. Yeah, Galerkin ROM doesn't do it. Data-driven model does do it. This is a tougher problem, tougher than the 2D flow past the cylinder. Last problem that I want to talk about is, well, I mean, this was really tough for us. So this is the turbulent channel flow. It's an academic test problem. Reynolds Tau 395 sounds little, but small. But actually, the Reynolds number, corresponding Reynolds number based on the bulk velocity is 13,000, 14,000. Not a whole lot. But we needed a lot of basis functions for the Galerkin ROM to do something, decent. We didn't do that. We truncated, so we used very few basis functions, and we wanted to see what closure works. And the answer is none. Well, what worked for us, turns out, is a hybrid modeling, in which we use some data-driven modeling, but we added just a little bit of, eddy viscosity, physical modeling to make it work. So really, this reflects what happens in LES. In LES, this hybrid modeling is very, it's quite used in practice because you can feed the data all you want, but in practice, so that's called a priori testing. But in a posteriori testing, in LES, the model that was great in a priori test might not work. So what people do is they add a little bit of physical kick into it. Yeah? That's what we did, and this is the one that worked for us. So the hybrid model and the constraint hybrid model, those work for us the best. Finally, so am I okay? I'm out of time. It's good. So this is a theorem that a paper that should come out soon. I think it's ready to go. So we basically prove that if you have accurate data-driven closures, right here, right hand side, you can get a low error. Yes, so the error is gonna be small. We can prove that. Yeah? So I think that this is a consequence of using Galerkin framework. It's mathematical, and the data-driven modeling that we're using is matching the closure terms. So having control of those helps us prove this type of results. Okay. Conclusions, realistic flows, I think, are under-resolved, even in biomedical flows. For this sort of modeling, this can be the case. LES-ROM is, I believe, a good approach. LES worked for decades for engineers, geoscientists, and so on. I believe it should work for ROMs. It does work. Yeah. The core of the principle is spatial filtering data. That's new. I guess people decades ago did not use that. And physical constraints. I really think that those are important. So simple, powerful method that is mathematical. So it's a Galerkin plus data, data-driven Galerkin. I really like this type of combination. This summarizes, so these are the papers that I really talked about. First, eddy viscosity, functional modeling, then structural modeling right here. And the last one in red is the data-driven part. The last paper is this year, appeared in Kamani this year. This is a good starting point. And if you're interested, just send me an email. I'll be happy to talk with you. Okay, this is all I got. Thank you.
Thanks to you, Traian, for your talk. Of course, the floor is open for questions. So unmute yourself and go ahead if you have questions.
Hello, may I go on, Andrea?
Luca, yes, of course.
Hello, thank you for the nice talk.
Thank you.
I have a lot of questions, but I have to keep it short, out of your interesting talk, of course. The first one is the following, but let me reduce to the following. Can you comment on computational costs using, let's say, data-driven against, let's say, conventional closure models, also including the fact that you have to use data and handle data to build this law. And the second, which is still related, is the following: how general can be these kind of data-driven closure models? Because I guess that this closure model is derived from data coming from very specific numerical simulation for 3D turbulent flow. Thank you.
Excellent questions. Excellent questions. Luca, these were excellent questions. So let me just say the second one, okay, I'll tell you right now. So the answer is we don't know. But the first one, so the computational cost, yes, very expensive. I mean, you're trying to match data. What we're doing, and this I didn't mention this, is that we use cheaper computational procedures. So for example, we, instead of using all the modes to approximate the closure term, maybe instead of R, we use 2R or 3R modes. So we try to cut computational costs as much as possible. There is an overhead. There's a computational overhead, and you know, it's a model. It's a correction term. So I think what we've done in our group is trying to cut corners, and it has not decreased the computational accuracy too much, the numerical accuracy too much. So I think that's the right way to do it. Don't beat it to death. Just try to approximate it and get the model that actually works. But you're right. So using data can be computationally expensive. The second question is actually a great question. So the answer is no. These are data-driven models. So you change the problem, you change the data, you change the model. Do I believe that we can get the universal model? I don't think so. You know, so we cannot get Kolmogorov theory. But what I believe we can get is actually a collection of models for different type of settings. For example, if you have flow past the cylinder at different Reynolds numbers, maybe there's a pattern in those closure terms. Then you move to lead-driven cavity. Maybe that's a different model, and then so on. So you have an atlas, an atlas of models for different type of flow configurations. I believe that that's possible. We have not done that. We're looking into that. So looking for patterns in these closure models, I think this is a great question, and I don't have an answer, but that's what we're looking at, maybe a collection of models.